I love homebrew computers, and the 1-bit vacuum tube abomination behind me, the UE1, is my very first ever homebrew computer. And while I absolutely adore this thing and am just over the moon with how it turned out, it's not exactly portable. It's very big, it's very fragile, and it's never moving from where it is on the wall because it's bolted to the wall. So I can't exactly pack it up and take it with me to an event and let people get hands-on with it. And that got me thinking I would really love to have a homebrew computer that I could set up at a VCF event and let people sit down and use it. And so I've been building a homebrew computer based around the CPU out of this, the TI-99. The TI-99 tends to get a bad rap, but if you could get your hands on a peripheral expansion box, or the PEB, this big beast down here, you had yourself a pretty capable system that could run some pretty impressive software. Like this one sitting here right now running Microsoft Multiplan. And yes, I realize that using a spreadsheet program to demonstrate the capabilities of a machine is like the most mind-numbingly boring thing I could have picked. But spreadsheet programs are tough, man. This one uses like every facet of the system, the disk drive, the 32K expansion, the full, like it's really kind of pushing it. But to have a usable spreadsheet program in the early 1980s on your home computer was pretty impressive. And there was a lot of other really good software out there like TI Writer or Parsec or Hunt the Wumpus or Munchman. So if you want to get into retro computing, my suggestion is the TI-99. You can still find these for ridiculous prices, and there is a thriving community based around these machines. Hop over to arcadechopper.com, my buddy Greg runs that, or jump over to the Atari Age forums where there's a very active TI-99 forum going on with people doing things that the original designers never thought possible on the TI-99. So why does it get a bad rap? Why was it not very well received? Well, TI made some interesting choices. They double interpreted everything by running it all through a GPL layer, or graphics programming language. Also, they gated all of the RAM behind the video display processor. It was a pretty weird design decision that ended up with a machine that was actually kind of slow. As much as I love it, I can admit that it is a pretty slow machine, but that CPU is what really fascinates me, because that is the TMS 9900, and that is a large-scale integrated version of the CPU out of the TI 990 mini computer. And just look how gorgeous it is. This thing is hiding out in a TI-99. Now, granted, the white ceramic package one like this is only in the TI-99-4. The later 4As had a black plastic package. But still, this one, this is the entire reason that I want to build a homebrew computer, if I'm being honest. But the TMS 9900 is a really interesting CPU in and of itself. Most notably, it doesn't have any registers inside of it. It has a status register, a program counter, and a workspace pointer. And that's it. I mean, there's a lot of other stuff floating around in there that we don't really care about because we don't have access to, but those three is pretty much it. All of the general purpose registers that the programmer needs access to are located in RAM, which seems like a choice. But let's take a step back and think about where this little TMS 9900 came from. This is a large-scale integration version of the CPU out of a TI-990 mini computer. And mini computers are all about multiple users and big storage. And this CPU has a bunch of stuff that's kind of centered around those concepts. By putting the registers in RAM, you can give each user their own set of registers. All you have to do is update the workspace pointer, because that points at the beginning of the set of registers. And if we just update that to a different location, that's a new set of registers that a different user can use. Now, there's a drawback to this, which is that your access to those registers is only as fast as your memory. And if your memory is DRAM, it's pretty slow. So oftentimes they used very expensive fast SRAM to hold all of these registers. But also this CPU has hardware level interrupts. There's 16 of them. So any user or a external device can hit a hardware interrupt and grab the CPU's attention. And things like big storage, like hard drives, can also do DMA. They essentially tell the CPU to hold on, and they take control of the bus and just shovel data directly into memory. So this CPU is set up for a mini computer, which makes it a little strange that they shoehorned it into a TI-99 home computer, but there's a whole lot of office and corporate politics that went behind that decision. But what this means for us is that we can pull this CPU out of a TI-99, slap it into a homebrew, and start making use of some of those features that the TI-99 never did, which is exactly what I'm trying to do here. And in the previous episode, we have the CPU, the clock, and we have 2 kilowords of ROM hooked up to this machine. And we were able to see that it was going through and executing instructions out of ROM at 3 megahertz with no problems. However, you can't really do a whole lot with just ROM because all of our registers are in memory and we don't have any memory. So today, I want to try and get these little guys into this machine. These are Mitsubishi M58725Ps. These are 16 kilobit or 2 kilobyte static RAMs, and we want to put 2 of them side by side so we can get a full 16-bit word because it is a 16-bit processor and it's going to be pulling things from memory 16 bits at a time. Now, if we do 2 of these, that's 4 kilobytes and only 2 kilo words for the CPU. So we're actually going to do 6 of these to give us 6 kilowords or 12 kilobytes of memory. Now, in order to access those chips correctly, we need to have a little bit of selection logic going on, which I've got outlined here. And I'm trying to keep it as simple as possible. Our RAM is going to live between memory address 1000 and 3FFE. And that's going to be decided upon by address 12, 13, 14, and 15. Notably, memory address 12 and 13 are how we know which of the pairs of memory chips that we want to select. Because like I said, we're going to use 6 of these ICs, which is 3 pairs. So we have 3 chip select lines that we need to worry about. However, if address 14 or address 15 go high, we need to disable this chip select completely. And because that's going to be deeper into extended memory and potentially different ICs that are doing things down that way. Also, we can control whether we read or write from those chips by just tying the write enable line directly across from the CPU. So thank you, CPU. You saved me a bit of logic there having to figure that out. So this is how I decide this is the complex logic that it's really not that complex. It's like 1 74LS00 and 2 74LS32s that build this out. And I've had some comments in previous episodes of people very confused about why I'm building things this way, using a lot of NAND gates and OR gates. It seems like a strange combination, and there's definitely way more efficient ways to do this. And the answer is that I have a lot of 74LS00s and 74LS32s. So I'm just trying to use stuff that I've already got to build this thing out. And I'm having kind of fun trying to figure out how to do things purely with NAND and OR logic. It's a weird combination that people don't normally use. So I've got 4 new boards, and I need to get these populated and get them plugged into the main bus over here, which means I need another backplane board. I got a lot of solder work to do. I'm gonna sit down and just get to work, hammer these out, get them all soldered up, get it plugged into that, and then we're gonna figure out how to test this stuff. The backplane is by far the most tedious to solder up, and also super boring to watch. Man alive, this isn't fun at all. Let's go say hi to the animals while past me does all the hard work. This is our boy named Sue. When we rescued him as a tiny kitten, his tail was already missing and he was in pretty rough shape. We bottle fed him, kept him warm, and helped him build his strength. So to paraphrase Johnny Cash, I knew he'd have to get tough or die, and it's that name that made him strong. This is Tin, Sue's sister. Her tail is also missing, so whatever took Sue's tail got Tin's as well. She was much healthier looking when we rescued the pair, and now she's just a big old sweetheart that never really strays too far away from us. This is May. She's a handful. She's a half golden, half King Charles Spaniel mix, and somehow she's simultaneously ridiculously smart and dumb as a box of rocks. And here's the real star of the show, our bunny, Coma. This is actually our 3rd bun, and she is by far the snuggliest. If I don't take at least 2 to 3 hours every day to sit down and watch TV with her, she gets real angry and won't even look at me. It's actually kind of hilarious. She's coming up on 7 years old now, so she's actually the oldest of the entire group. Although every once in a while during the end credits, I'll put a video of our very first bun up, and that's Kono. She passed several years ago, but the Usagi Electric logo is based on her. So she'll always be hanging out with us while we're out here working on cool old stuff. I'll also sometimes slip in some videos of baby bunnies on the occasion. These are all wild cottontails that we've rescued. We live out in the middle of nowhere, and Sue, Tin, and May tend to find rabbit nests regularly. We've rescued, rehabilitated, and released back into the wild more than a dozen wild cottontail babies over the years. And there we go, all done, and these things turned out looking beautiful. This one right here, it has got our chip select logic on it. We've got the two LS32s and the single LS double aught, but I also slipped a bunch of LEDs across the top here. These LEDs are going to be showing the hold and hold acknowledge, the wait signal, the ready signal, the data bus in, memory enable, and write enable signals. So pretty much anytime data is moving through the system, we should see these flickering around and doing fun. I just wanted some like blinking lights. I thought they looked neat, and I had a little extra space there on the top, so that's why I did that. On this card here, these I've got 3 of these. All 3 are identical. They just hold the 2 ROMs and a little header down here that I could do some wire wrapping on so that we could do a chip select. So this is chip select 3, and then we've got chip select 2 and chip select 1. So we need to get these slotted into here and smoke test the thing, and hopefully nothing breaks. This is genuinely the first time I've tried powering all 8 boards up at the same time. I have no idea what's gonna happen, but I'm hoping to see some blinking lights. Here goes nothing. Well, we definitely have some blinking lights. I guess that's good news if I hit reset. Yeah, it's running. Well, nothing caught fire. That's a good, promising start, but now we got 2 problems that we got to try and overcome. The first is that it's still running the program that we put in ROM from the previous episode, which is just jumping to 3 locations in memory over and over and over again. But all 3 of those locations are within the ROM memory address space. So we're not even touching the brand new static RAM that we put in there. But the second problem is that even if we were exercising the static RAM, like how could we tell? This computer doesn't have any way currently to get output to the user. So I think what we got to do is we've got to write a new variation of the program that we wrote in the previous episode. And what that program did is it just jumped to 3 different locations over and over and over again. And those locations were not in sequential order, but they ended up in such a way that the memory address bits toggled one after the other, but never overlapped. So let's take that and translate it over to RAM. But that's like, things start getting a little difficult when we do that because RAM is volatile. So we have to essentially store our program in ROM and then copy it over to RAM after the machine has started up and been reset. So I've got a program here that I think will get that done. I'm starting to follow proper TMS 9900 assembly here. So the first line says RORG, and we're putting that at 000. This is a relocatable origin, and this just tells the assembler where the following code is going to start at. And then we have 2 lines that say data. That 1000 is our workspace pointer. This is telling the CPU where all of our registers are located, and 1000 is right at the beginning of our static RAM. So now the CPU is going to be looking for registers in our static RAM. We're already using it. That's awesome. Then 80 is where the following code is going to live, and that's our program that's on ROM. We do the RORG again, and then we have a bunch of load immediates right in a row. So we start with a load immediate 1. So we're going to load whatever value we specify directly into register R1, and that value is 0460. And then we're going to do a load immediate register 2 with a value of 3000. Now 0460 is a branch instruction, and then the memory address that it will unconditionally branch to is 3000. And then we're going to load immediate register 3 with the 0460 again. This is a branch instruction, and the address specified is 2800. We're going to put that in register 4. And then we're going to load register 5 with the value 2800, and then we're going to copy the value stored in register 1 into the memory location pointed at by register 5. So register 5 has a value of 2800. So at that memory location, we're going to place the value 0460. And then we just move right on down the line. So what this program is going to do is it's going to copy some values from ROM into static RAM, and then it's going to jump to those locations in RAM and start executing whatever those values tell it to do. And what they're telling it to do is essentially just jump back and forth between two locations in memory. Memory address 2800 and memory address 3000. It's just going to be going back and forth between the two, and we should be able to see that on the scope as two memory address bits flipping on and off over and over and over again. And this seems incredibly simple, but this actually hits every single aspect of everything that we've built so far. This is going to hit all 6 of those static RAM chips that we put in. You properly use the chip select circuitry that we've built, and it's going to flex our ROMs. So like, this is, I think, a pretty good test program. So I just need to take this and get it onto those ROMs somehow. This is just words on a piece of paper. This is meaningless to this thing. And in the previous episode, when I put a program on those ROMs, I actually hand assembled it. So I looked up in the book what each instruction was in binary and then wrote that binary out in a hexadecimal file. But I don't think that's going to work for this, and it's certainly not going to work for much larger programs that we're going to have to get into in the future. So we got to figure out a tool chain for how to take words on a piece of paper and turn them into raw binary bits that we can put onto the ROMs in here that the machine can understand and execute. And in order to do this, we're going to use my Linux laptop here. Now, before you hop into the comments and start telling me about how to properly use Linux with the autocomplete and up arrow and all these different shortcuts to make the Linux experience move way faster, I am well aware of all of those. I type everything out by hand when I'm filming on purpose so that those that aren't familiar with Linux can still follow along and see what's happening. All right, so here we are. We can see that we're in the folder here, and zflex.asm is actually my assembly here. And if I do cat zflex.asm, we can see that's our little page right here. What we want to do is we want to assemble this, and I'm using a collection of tools created by Dave Pitts. He has a wonderful collection of TI 990 mini computer tools. I'll put a link in the description below. And he wrote an assembler and a linker, and we're going to use both of those. The assembler is, I think I'm going to have to do a sudo here, /asm990, and we want to create a listing file, so we're going to do a -l, and the name of that listing file is going to be zflex.list, and then we also want to create an output object file, so we're going to do a -o, and that's going to be zflex.obj. And our input file is zflex.asm. So the object file is what the assembler outputs, and that's not quite binary. It's something that the linker will be able to read to create the binary that we need to create. So we'll go ahead and hit return on this. Looks like it ran correctly. If I do a ls to c, we can see that we now have a zflex.lst and a zflex.obj. If I do a cat zflex.lst, we can see that it created this output listing of our program, and we can see memory addresses on the left and the values that are stored at those memory addresses. I mean, it's really cool. You can learn a lot about how assembly equates to machine language via a listing file like this. But if we do a cat on zflex.obj here, we can see that that's very different. That doesn't match up with the binary that we're seeing in the listing file. So we need to take this object file and actually create a binary file from that. And we're going to do that with a ./lnk990. And we're going to do a -a, and this creates an a.out type file. This is what we need to create the specific binary that we're going to write directly onto the ROMs. And then we're going to do a -o, and then our binary file we're going to call zflex_o.obj, because ultimately it is still an object file. So zflex.obj now is our input. Let's go ahead and hit return on that. Looks like it ran correctly. If we do an ls, we should be able to see zflex_o.obj in there. And I should be able to see the raw hex of this if I do a hexdump-c, and then I type in zflex_o.obj. Helps if I spell it correctly. So now I'll do an up arrow, and we'll go back and drop drop that out. Okay, so if we remember back to our code listing here, the very first words should be 1000 and 0080. And we can see 1000 and 0080, but they're not the very first words. They're a full 16 bytes away. And that's because the a.out type file that it creates always puts a header on the top. So what we need to do is we need to delete that header, and then everything will line up perfectly. And we can do that with dd, and then we do if, which I think is input file, equals zflex underscore o.obj. And then OF, which is output file, equals zflex.bin. And then we want to do BS equals 16. So for 16 blocks, we're going to do a skip equals 1. So all we're doing is we're copying from the OBJ file to the binary file, and we're skipping the first 16 bytes that'll be on there. So let's go ahead and hit enter on that. Yeah, looks like that worked just fine. Let's do a hex dump -c zflex.bin. And yeah, there we go. We're starting at 10000080. That is all correct. And then we can see our huge collection of code down there on the bottom. So, all right, that's great. We're making progress. This is the binary file that we need, except we got to remember that the TMS 9900 is a 16-bit machine using two 8-bit ROMs in parallel. So I have to split this file up into high byte and low byte. Thankfully, Linux has a ton of utilities that you can do that with, and one we're going to do it with is srecord. So we're going to do srec_cat, and then we're going to do a -o, and we're going to call this zflex_low.bin, and we're going to call this a -binary. And then the file that we're using as input is zflex.bin, and that is also a binary file. And then we want to split this, and we're going to give it the parameters of 2, 1. And we go ahead and run that. And then we want to run that again for the high byte. So I'll hit the up arrow here. We'll backspace out low, change that to high, and then we'll change the 1 on the end to 0, and then run that again. Now if I do an ls, we should have a low byte and a high byte. I now need to just take these two binary files and copy them over to the ROMs. And in order to write that binary file down to the ROM, I'm just going to use the TL8662 Plus here. This is a cheap little ROM burner that you can find pretty much everywhere. But there's one big downside to this, and that is that the official software for it is Windows only. And since we've done everything within a Linux environment so far, I would like to stay in that Linux environment. Fortunately, there are some very smart people out there, and I'm using the Mini Pro utility written by David Griffith. This is, I'll put a link in the description below again, but this is a utility meant to interface with this TL8662 Plus, and you can run the whole thing from the command line here. So we're just going to invoke it by typing Mini Pro, and we need to give it some commands here. So we're going to do -p to specify the device, and our device is the ROM. That's going to be an XLS28C16A. We want to do a write, so that's going to be a -w, and we're going to do a -s to tell it to ignore the size difference, because the ROM is going to be a lot bigger than the size of our binary file. Our binary file is actually very small, so it's just going to fill in the rest of that with FF or 00 or whatever it picks. And then the file that we want to send it is zflex_high.bin. And then we're just going to hit enter on that. And a little bit of confusion going on. I got my -s and -w, I think, intersposed here. So we want to do a -s first and then a -w. Oh man, it sure is picky. All right, let's hit enter again. There we go. Now it's writing. It helps if you type things in the correct order. So we can see it said the incorrect file size, but that should be okay. We can actually read this back now by pretty much doing the same thing, only instead of a -s and a -w, we're going to do a -r, and we're just going to drop that into something called like test.bin. So it should read that code back. Now if I do a hex dump -c of test.bin, but we can actually kind of compare this if we do a hex dump -c on zflex_high.bin. And yeah, there we go. Those two files are identical. So we have successfully written the high byte to our high byte ROM. I just need to pop out the low byte ROM, write the low byte file to it, put it back in the machine, hook the scope up, and hopefully everything works. I've got the scope here set up to just 2 traces. This should be memory address 11 and memory address 12. I believe these are the 2 that should be twiddling over and over and over again. So, oh, I don't know, the moment of truth, here goes nothing. Hopefully it works. Oh, I think I destroyed a ROM. Oh no. Oh no, all right. I am apparently trying my level best to burn these ROMs to the ground. Always check your work. You can see that I installed this ROM with 1 pin offset, just hanging out in the void here. Those poor ROMs, man, they've really been put through the ringer. I've got them back in there, but if it doesn't work right off the bat, then that'll be our first suspect here. So we'll go ahead and flip the power switch on. Well, we've got something that looks a little promising on the screen here. So let's go ahead and speed that up a bit. And yeah, that's exactly what we wanted to see. The memory address lines are toggling perfectly in and out of phase. That's awesome. For this to be running, like, this is epic. Like, I can hit the reset button and you can see it goes away. This is not a scope shot. This is like running live. It comes back. In order for those 2 memory address lines to be toggling exactly like they are, that means that my code, the program I wrote, has to be working. We're using everything on this homebrew computer and it's all working. That's so cool. So what's next? We can't obviously keep having the scope on here to determine that things are working. We got to get a data terminal on this. So we're going to get a UART hooked into this, and then we can get it printing things on a data terminal. And the primary data terminal that I'm going to use for this is the cute little TI Insight over there. And because I'm going to use that TI Insight, I'm going to change up the design of all of this. I mean, the board and the like big mean wells hanging out the back here was just kind of a temporary thing to get us off the ground until I kind of knew what direction I wanted to run in with the overall final shape of the thing. This project is shaping up just beautifully. I'm absolutely in love with this. It looks cool. It works like a top. Amazing. Not only that, my code worked right off the bat. Like, what are the odds of that? I didn't even get that wrong. That's what a day. What an awesome day. So thank you all so much for hanging out with me on this excellent day, and I hope to see you in the next one.